Hello, everyone. Thank you for coming to my pre-workshop talk for the Quantum Oscillations and Insulators workshop. My name is Patrick LeBarre, and I'm a grad student at UC Santa Cruz working with Dr. Arthur Ramirez. And today I'm going to be presenting data from our week-long run at the National High Magnetic Field Lab in Tallahassee on high-quality aluminum flux growth samples that show evidence for specific heat quantum oscillations in samarium hexaboride. And so I'm not going to spend a lot of time motivating the system, as I'm assuming most of you all know why there's so much excitement around samarium hexaboride. However, just to give you an inkling of why we got interested, so the system shows the Haas-van Alphen oscillations, but not Shubnikov-de-Haas oscillations. And there's a large debate as to the origin of these oscillations, especially between flux and float zone growth samples. So our main question was, is this a direct effect of the density of state? And so we wanted to measure the high field specific heat, as that's a direct probe of the density of states that is not susceptible to scattering effects or demagnetization effects. And so utilizing the highest precision measurement of specific heat for these samples, which have extremely small thermal relaxation time constants, one needs to use AC calorimetry, a notoriously challenging measurement, especially in high fields. And so what we're going to show is the tools developed using AC calorimetry for small oscillation detection. And so with that in mind, here I have a couple of isotherms. So from temperatures from 1 to half a degree between fields of 18 to 31 Tesla, we have the specific heat shown here, C versus 1 over H. And it's based on this signal, it's not surprising that if we're going to be searching for oscillations, we're going to have to put some work in. But bear in mind that the direct observation of the fact that we don't have a direct observation of oscillations is not an indication that they're not present at these temperatures and fields. And so moving forward to look for extremely small signal oscillations in this data, we have to take into account a few important factors. First being the correct choice for background specific heat subtraction, as when dealing with low signal to noise data, using high order polynomials can actually lead to induced oscillations in your residual specific heat that are artifacts of the background subtraction. Secondly is that the data is most commonly taken linearly in external field, where we are looking for oscillatory phenomenon within Lifshitz-Kosevich theory that is periodic in 1 over field. And so that actually introduces a non-uniform sampling rate. And so one needs to take into account more complex frequency analysis to make sure that the data is appropriately binned. And then lastly, depending on the frequency analysis procedure, one needs to have some form of statistics to apply to the peak selection criteria so that you can appropriately attribute certain phenomena to certain frequency peaks. And so that being said, we then, based on the similar curvature for all of our isotherms at these temperatures and fields, decided to use a sigmoid function shown in the top left here, which is a Fermi-Dirac distribution. And so we chose this primarily because it's over any field range, a non-oscillatory function, and it has considerably fewer fit parameters than higher order polynomials. Where here, again, I want to stress that we are dealing with aluminum flux ground samples, and the field alignment in the both of these plots is with H parallel to the 001 crystallographic axis. And so subtracting our sigmoid function to the lowest temperature data here, where that was actually typo, it's actually 0.6 Kelvin. To the eager eye, looking at the right here, our residual specific heat versus inverse field, it seems like there may already be oscillatory components. However, one needs to perform a rather rigorous frequency analysis to verify that. And so that leads us to the second issue that needs to be taken into account, in that we are taking data linearly in field. And so here I have shown a discrete Fourier transform and a non-uniform discrete Fourier transform of this data set on the right, the residual specific heat versus inverse field for one of our runs. And so here it's important to note that the discrete Fourier transform fails when you have non-uniform data sampling, because there's essentially a loss of phase information, and you also falsely bin data for frequencies that the data does not represent. And so one way that this can actually manifest in the resulting frequency spectrum is significant peak frequency shifts. So for the discrete Fourier transform, the peak is actually not properly represented and is shifted by about 100 Tesla. And so that's just one of the issues if you were to proceed with a discrete Fourier transform. And then one added benefit of using the non-uniform discrete Fourier transform is that you are actually more susceptible to high frequency oscillations, and we have this increased high frequency detection even though we still have the same number of data points. And so with that, one then needs to go on to choose the appropriate form of non-uniform discrete Fourier transforms. And so we stumbled upon the Lom-Scargill method, which has been drastically popularized by colleagues in the astrophysics and cosmology areas of research, as they often deal with non-uniform sampling with restricted windows for observing. And most importantly, for the Lom-Scargill method, it is generally the most robust for sinusoidal periodicity. So within Lifshitz-Kosevich theory, that's exactly what we're looking for. Where here, I just want to take a moment to say that the Lom-Scargill method is primarily a combination of Bayesian statistics and least squares fitting at each frequency point, combined with a Fourier analysis. And so with that, one needs to have some form of statistics to apply to their peak selection criteria. So within the Lom-Scargill method, there's a very useful metric that comes out of it known as the false alarm probability, which is essentially the probability that the data at any given frequency is composed of random noise that is Gaussianly distributed. And so if you weight your frequency spectrum based on the inverse of this false alarm probability, you get a great measure of your noise floor, and you are also able to easily identify the main contributing frequency peaks from your power spectrum. And so now that we have established a fairly robust analysis for identifying frequency peaks with low signal to noise data, we then want to go on and try to model the amplitude of oscillations with the residual specific heat data, and the growth of or reduction of the amplitude of those oscillations, so the envelope of those oscillations over a specified field range. And so looking at the same residual specific heat data with H parallel to the 001 crystallographic axis, we are able to fairly accurately model not only the growth of the amplitude of the oscillations, which we see here is actually an increasing amplitude of oscillations upon reducing field, as we're looking at C versus 1 over H, but we're also able to model the magnitude of the peak-to-peak oscillations at any point given in our measured field range. And so now that we have appropriately identified a frequency and used a physical model to set the amplitude of the oscillations and the envelope of the oscillatory data, we now want to go ahead and say, how does this compare to the frequency spectrum of samarium hexaboride? And so here you'll see the gamma, epsilon, rho, and rho prime Fermi pockets as computed in density functional theory and rigorously identified through de Haas van Alphen measurements for flux and float zone growth samples. And we see in the very limited data set that we were able to acquire, again, as a result of the complexity of this measurement and the minimal runtime that we were allowed to take data with, we see over almost the entirety of our measured points great agreement with the expected frequency spectrum for samarium hexaboride. However, we do have one outlier looking at roughly 45 degrees along the 111 axis at 1500 Tesla. And so, seeing as these are aluminum flux grown samples, one then wants to ask, how does our data compare to aluminum? However, I just want to identify all of the residual specific heat data that I have shown thus far is for the run taken with H parallel to 001 with a frequency of 695 Tesla. And so we then move on to ask, how does this compare to aluminum? And so shown here is the frequency spectrum from aluminum for the gamma Fermi pockets for the 0th black lines, first blue lines, and second orange lines harmonics. And we see that while there are some points that show good agreement with the oscillation spectrum for aluminum, there's also multiple points that do not. And so we then ask the question, if there is this identification of the same frequency points, can we model the amplitude and growth of the oscillations with published materials parameters within the Lifshitz-Kosevich theory for aluminum? And so going back to our residual specific heat data for that one run specifically, if we were to model up to 50% of the sample to be composed of aluminum, there is no way for us, one, to model the growth of the oscillation envelope, and two, to model the peak-to-peak amplitude at any given field within our measured field range. Where here it's important to note that the published parameters that we are using within Lifshitz-Kosevich theory would be an effective mass of 0.13 electron masses for aluminum and a Dingle temperature of 0.9 Kelvin. And so with those published materials parameters, we are not able to model our data. So then we go back to our best fit range, where we are able to see shown here that we can set limits on the maximum range of observable oscillations within the Lifshitz-Kosevich theory. And so looking at the red curve, which is the peak-to-peak envelope is set by those black dash curves, that is looking at the maximum possible oscillatory phenomenon in the zero temperature limit. So in this case, we are no longer taking into account damping effects due to phase smearing and electron scattering. So if we were then to incorporate those in the finite T limit, where we had shown earlier our best fit values within Lifshitz-Kosevich theory is this blue curve, we are then able to extract the materials parameters shown here for all of the points that were shown on our previous oscillation spectrum, where for this run specifically, we find that for a frequency of 695 Tesla, the best fit range, or the best fit values for the effective mass is 5.3 electron masses and a Dingle temperature of 0.3 Kelvin. Where here it's very interesting to note that the Sommerfeld coefficient for samarium hexaboride, being 5 millijoule per mole K squared, is in great agreement with our effective mass determination within Lifshitz-Kosevich theory. And so what it appears, especially if we look at the full range of our limited measurement between 0 and 45 degrees, we see that the effective masses for all of our data sets corresponding to multiple Lifshitz-Kosevich fits range between 4.8 and 6 electron masses, again, consistent with our Sommerfeld coefficient. And so what we have shown is that within Lifshitz-Kosevich theory, aluminum inclusions cannot describe our data. And so for these high quality aluminum flux grown samples, it seems that there must be something else that is more intrinsic to the samples that is going on. Within Lifshitz-Kosevich theory, we can then also set a amplitude envelope for the largest possible oscillations to help further theoretical models. And here we have shown that there is evidence for intrinsic quantum oscillations in these aluminum flux grown samples that is not possibly from aluminum within the standard Lifshitz-Kosevich theory. And so it appears that we have heavy excitations. These intrinsic quantum oscillations are arising from heavy excitations that are bound to the same Fermi pockets. And so with that, I'd like to acknowledge our funding sources, the NSF and DOE. I'd like to thank our collaborators, Andreas Rud at Stockholm University, Scott Hannes at the National High Magnetic Field Lab, Nathaniel Fortune at Smith College, Priscilla Rosa at Los Alamos, Zach Fisk at UC Irvine, and of course my advisor, Art Ramirez at UC Santa Cruz. With that, I thank you for your time, and I look forward to the many talks of this workshop and discussing these data.